Hello everyone. In this video, we'll be going over the tutorial in Adminum for the sum and difference in cofunction identities. It should be your week 2 tutorial. And this is my second time doing this video because my PowerPoint didn't show on the last one. So hopefully this one goes even better. So if you go to your weeks, it should be this week 2. It should be unlocked. You click on your tutorial. So we're just going to walk through these. Now, before we start, I will say that you should be using this video wisely. So what that means is you should, anytime there's a question, you should pause the video, try the question on your own, and then restart the video to check your work. Okay, so you should not just be going through and grabbing answers because that's not going to help you on the test. So make sure you're actually comprehending and trying this stuff on your own. And feel free, last time this video was about an hour, so if you want to break it up and do it in 2 intervals or whatever works best for you, you use this video the best way it works for you as a learning tool. So this first video, or this first slide on the tutorial, is just an introduction video for Adminum. You don't need it. Here's what we're learning: the sum, difference, and cofunction identities. So where are those on your identity chart? I highlighted them in orange. So sum and difference is right here. So they use A and B, but we know that that could be any letter. It could be X and Y. It could be theta and some other letter. So just keep in mind, it just means if you're adding or subtracting 2 angles inside your trig function, how do you break it up to be sine and cosine of each individual angle? Okay. And then cofunction identities is over here on the right side next to Pythagorean identities. And we'll get into that later, but just so you know, those are the 2 formulas we're going to be using. Next slide is the objective. We just talked about what we'll be doing. And that's an introduction video. You don't really need it, but you can watch it if you want. Just pause my video and watch that. Okay, so here's the introduction problem. So it says you're an engineer for an electric company and you have been asked to find the height of an electrical tower that needs maintenance. 2 cables run from the tower to a stake of 5 feet from its base. The shorter cable is attached 5 feet up and makes a 45-degree angle with the ground, and the tower, the longer cable, makes a 30-degree angle with the shorter cable. How can you determine the tower's height? Notice the line represents the height of the tower is opposite from the 45 and 30-degree angle. Solving this problem involves finding trig functions of sums and difference of angles. And so in this lesson, we'll figure out a way we could solve this problem. So if you think about it, just to kind of get our brains going, 45 degrees is this lower angle, 30 degrees is the top angle. So if we want to know the height of this whole big triangle, what's the angle opposite of this height? It's for the big triangle, you'd have to add these together. So 30 plus 45 would give you 75, and that's the angle for the big triangle. So that's going to tie in because what we're doing for sum and difference is we're taking an angle and breaking it up to be 2 angles that you either add or subtract. So 30 plus 45. And then you could use a sum and difference identity. So they're going to go back to that problem towards the end of the tutorial, but just keep that in mind. So here they just talk about what I was just saying. So how could we break up an angle? So it talks about how if you want to find cosine 75 without a calculator. Well, normally if you're not using a calculator, you're going to use your unit circle if they give you an angle. And 75 degrees is not on the unit circle. So what they do is you say, okay, well, what could we break 75 up to be, either adding or subtracting, that equals 75 using 2 angles from the unit circle? For example, they did 30 plus 45 or 120 minus 45. I always try to stay within that first quadrant, and then if you can't find anything within that first quadrant that equals that whatever original angle, then I go on and look at the rest. So you can pause and read that if you would like to, but that's the goal of that slide. Okay, so here what they're doing is they're deriving our first sum and difference identity. So I'm not going to spend too much time on this because you don't need to know how to do this on your own. They're just showing it to you. But they use the distance formula you learned back in geometry. When you subtract the x's squared plus subtract the y squared, and you get the distance of a line. And then they just do some algebra to simplify it. And then if you go to the next slide, they're working with that same thing. And now they use distance formula, but with another setup. And if you go through this and you want to understand it, you have any questions, let me know. But I don't think I'm going to use the time in the video to go through this. But they come up with another expression for the length of AB. So if both of those things represent AB, then you can set them equal to each other. And then they just go through and do some algebra and simplify this. And now it says we have successfully derived the difference identity. So this cosine u minus v. So if you're so they use u and v. Our formula uses a and b. Doesn't matter. It just means if you're subtracting two angles inside cosine, you could break it up to be cosine of the first angle times cosine of the second angle plus sine of the first angle, sine of the second angle. Next one is just showing you how you could derive all the other ones. So if you're adding inside cosine, it would be this formula. And then down here, it gives you all of them. So if it's sine and you're adding two angles inside of it, you would break it up like this. So it's sine of the first times cosine of the second plus cosine of the first times sine of the second. And then if it's minus inside sine, it's the same formula, but it's minus here. And then cosine, we already read one of them. But it helps to see the patterns in there. You do have your formula chart and your identity, so you don't have to memorize it. But go very careful. You should only be using sine and cosine for each angle once. Okay, that kind of helps me make sure I'm not doing something wrong. And then tangent, those are kind of different. It's a fraction. And if you're adding inside tangent, you break it up and do tangent of the first angle plus tangent of the second angle divided by 1 minus tangent of the first angle times tangent of the second angle. And then if it's minus inside originally, then it's minus on top and plus on bottom. So those are your sum and difference identities. Let's see. Now this slide, is just making sure you match the identities right, that you don't have it mixed up. So you can use your identity formula chart and just slide. And we know that this one would go with whichever one, and you are just using this formula chart. Okay, so I'm gonna have you can do that one. So pause the video, complete this slide, and then you can keep going. So the next slide is talking about how do we know that this actually works. So it says, let's apply the sum and difference identity for sine of 120 degrees angle. We already know this value, correct? Because 120 degrees is on the unit circle. It is right here. And the sine value would be the y value, which is square root of 3 over 2. So we already know sine of 120 equals square root of 3 over 2. So we're going to see if we use the sum and difference for 120, will it also equal square root of 3 over 2? So it asks the question, how can you express 120 degrees as the difference of two angles from the unit circle? That's what they mean by that you know. So they say one option, if we're trying to do subtraction, is you could do 150 minus 30. When you're doing this on your own, you kind of just got to play around with it and guess and check and try different angles on your unit circle and subtract them or add them depending on the problem to equal the original angle. So we can see that we could break up 120 to be 150 minus 30. So since we broke it up to be subtraction and it's sine, we are going to be using the second sum and difference formula. So we're going to do sine of the first angle times cosine of the second angle minus cosine of the first times sine of the second. So that's what they do here. And then you just use your unit circle to evaluate this. So sine of 150 degrees would be the y value at 150, which is 1/2. Cosine of 30 is the x value at 30 degrees, which would be square root of 3 over 2, minus, and then cosine of 150 would be negative square root of 3 over 2, and sine of 30 would be 1/2. So you can go look at your unit circle and make sure that that makes sense to you. And so when you're simplifying these order of operations, you got to first multiply each set of fractions. So when you multiply fractions, you multiply the top and the bottom. So 1 times square root of 3 is square root of 3. 2 times 2 is 4. Now here, when we multiply this set, we can see that this is going to be minus. This is going to end up being a negative because it's a negative times a positive. So minus and negative, they changed to plus. And then they multiplied these fractions, square root of 3 over 4 again. Well, then on the top, square root of 3 plus square root of 3, you cannot add the inside numbers of square roots. So you just, because they're the same square root, you can write it as 2 square root of 3. over 4, and then simplify the 2 over 4 to be 1/2, which is square root of 3 over 2. So we can see that that equals that original answer of sine of 120. So whether you break it up or use the unit circle, they're the same thing. Then they use the sum identity for the same angle. They say, okay, what two angles on the unit circle add to be 120? Well, they use 90 plus 30. And so then they're using the sum identity for sine, which is similar, but it's plus right here. And you can see that if you do that with these two angles and use the unit circle, you end up with square root of 3 over 2 again. So it's all the same thing. It doesn't matter what you pick as long as it equals that original angle. Okay, the next slide is talking about clearly we don't need sum and difference identities to determine that trig value of 120 degrees because that was on the unit circle. We should have already known that. Rather, the sum and difference identities are useful for finding exact values, such as sine of pi over 12 or 75 degrees or 165 degrees, because those are angles. You can do degrees or radians that are not on the unit circle. Okay, so when do we use this? It's for angles that are not on your unit circle, but you break it up to be two angles that are on the unit circle. So let's spend some time looking at the radians, because degrees is pretty easy to just guess and check and find two angles that add or subtract to be that original angle. But now when fractions get involved, you got to kind of think through that. So let's think about this problem, sine of pi over 12. If I'm looking at my unit circle and I'm looking for two radians that equal pi over 12 when I add or subtract them. Well, when you add and subtract fractions, you need a common denominator. So what I would do is go and convert. I would start with just the first quadrant. And if none of those work, then you could go convert more. But normally that first quadrant will get you what you need. So the common denominator for using these first quadrant radians would be a 12, right? We could take all of these and get them to have a common denominator of 12. So I take pi over 2, multiply by 6 on the top and bottom, and turn it to 6 pi over 12. Pi over 3 to get a common denominator of 12 would be 4 on the top and bottom, and get 4 pi over 12. Pi over 4, multiply by 3 on the top and bottom to get 3 pi over 12, and pi over 6 would be 2 times 2 to get, 2 over 2 to get 2 pi over 12. So now these are all your first quadrant angles with a denominator of 12. So now it's going to be easier to see, okay, using these over 12 angles, which to add or subtract to equal 1 pi over 12 or pi over 12. So let me go to the next slide. So it says if we're trying to find sine of pi over 12, we need to find two angles. That's what I just said. The add or subtract to be pi over 12. Here I converted them again, but it's the same thing from the other slide. So there is more than one correct answer. Okay, so this is just an example that I picked, but you could pick another one and get the right answer. So I said if I subtract 4 pi over 12 minus 3 pi over 12, that would get me pi over 12 or 1 pi over 12. So what does that mean though? Go back and convert them back to the original ones. 4 pi over 12 was originally pi over 3, and 3 pi over 12 was originally pi over 4. So now we know pi over 3 minus pi over 4 would equal pi over 12. So I can rewrite my original problem. It was sine of pi over 12. Now I can break it up to be sine of pi over 3 minus pi over 4. And now I can use my difference formula to evaluate that. So hopefully this common denominator and subtraction math makes sense. If you have any questions, feel free to reach out to me. So what they did is they broke it up to pi over 3 minus pi over 4. And then they used their difference formula and then use the unit circle to get those values. And so when you're multiplying, I want to make sure we're good with our square root math. When you're multiplying square roots on the top, I don't have to be on the top, but when you're multiplying square roots, you can multiply them to be one square root. Okay, square root of 3 times square root of 2 is square root of 6. So then it'll be over 4 because 2 times 2. And you have minus 1 times square root of 2, square root of 2 over 2 times 2 is 4. Now these have a common denominator, so we can subtract the numerator, but you can't actually add and subtract square roots. So you'll just have to leave your answer square root of 6 minus square root of 2 all over 4. That is the first one. So then here they do 75 degrees, which they break it up to be 45 plus 30. Use the cosine addition. formula, which would be this third one, cosine of the first times cosine of the second minus sine of the first times sine of the second. And then they use their unit circle, simplify it the same way, and you get your answer. So notice those are the same because pi over 12 and 75 degrees are actually equivalent. Actually, no, they're not. That is not true. I take that back. Okay, then they do a tangent one, so 165 degrees. They decide that you could do 45 plus 120 from the unit circle. So then when we use our tangent formula, it'd be tangent of 45 plus tangent of 120 divided by 1 minus tangent 45 times tangent 120. So tangent 45, let's make sure we remember how to do tangent. What's the ratio for tangent? Y over x. So 45 degrees, the ordered pair is this, square root of 2 over 2, square root of 2 over 2. So if you do y over x, and they're the exact same number, anything over itself is 1. So we know tangent of 45 is 1. What I would suggest is if you have this formula chart printed out and you have the unit circle at the bottom, I would go write the tangent and cotangent values by all those ordered pairs because it's going to make your life a lot easier. You don't have to, but I promise it'll save you some time in the future. So we know the tangent value here is 1. Now we need also the tangent value of 120. So if we go to 120 and we're going to do y over x, and so because they're both over 2, when you do y over x, those over 2's would cancel out. So you can do keep, change, flip if you want, but you're going to see every single time those over 2's will cancel. So you really just have square root of 3 over negative 1, which would be negative square root of 3, which is why this changed to minus, because it was plus a negative. And so they just kept the top the same, and then on the bottom, because it was 1 times negative, that ended up being plus on the bottom. And then don't worry about what they did here. You don't ever need to go that far. You can just leave it as a fraction like this. Okay, the next slide I think is gonna, oh no, this slide is just showing you that you could check your work in your calculator. So what we could have done is you could type sine of pi over 12 in the calculator if it's in radian mode, and then you could type this answer in the calculator and see if it's the same decimal. But that's not going to help you on your test other than to check because you can't type a decimal as an answer. So, but you can check your answers that way. Okay, slide 15 is showing you a different type of problem using the same formulas. So if we read this, it says the sum and difference identities can also be useful in solving for angle measures. Consider the diagram shown. How can we use a sum or difference identity to find the exact value of angle A? So angle A is this whole angle for the big triangle. First, look at the smaller right triangle with legs of 5 and 12, and then, oh, okay, well, hold on, we're not going to do that yet. So we know that if we're talking about just A, then we could break that up to be 30 plus x, right? Because if you add these two smaller angles, it equals the whole larger angle. So they rewrote their problem. Instead of cosine A is cosine of 30 plus x. So then that means you can use your cosine sum identity, which would be this third one. And so they used that identity and broke it up to be in terms of 30 and x. So now cosine of 30 and sine of 30, we know those values from the unit circle. What we don't know is cosine x and sine x. So what they did is they said, okay, well, this is a right triangle. If you just look at the small bottom triangle for this angle x, we could use SOHCAHTOA. So we know the opposite side of x is 5, the adjacent side is 12. We are going to need this hypotenuse for this small right triangle. So that's what they talked about on the top. They said if your legs are 5 and 12 using Pythagorean theorem, we could solve and get a hypotenuse of 13. So that hypotenuse would be 13. So now if we use SOHCAHTOA, we know cosine of this angle x is adjacent over hypotenuse. So the adjacent leg next to x would be 12, and we just said the hypotenuse is 13. So cosine x is 12 over 13. Now sine of x would be the opposite leg over the hypotenuse. So the opposite leg is 5. over the hypotenuse is 13. So now we know, even though we don't know what the angle x is, we know cosine x and sine x are those fractions. So now we just plug everything in to get what is cosine A. All right, so we said cosine 30 is from the unit circle, square root of 3 over 2, times cosine x, we said is 12 over 13, minus sine of 30 is from the unit circle, 1/2, times sine x is 5 over 13. And then they just multiplied each fraction set together and then subtracted the numerator. Okay, this next slide is walking through how to use it. And I will say the way they word it's kind of confusing. So I'll go through and do this one with you. But if you want to, pause the video and you can try this on your own. So it says, how could we use the known values of cosine 120 and cosine 135 to find the exact values of cosine 225? So what's the first thing we're going to do? In your own words, you should think, okay, well, I know I could break up 225 equals 120 plus 135. So what do they, so you can't just add those cosine values together. That's not how it works. It says use an identity to set cosine 225 equal to the known values. And use the difference of the product. I don't think that's the right formula. So it's use this identity. We always want to use an identity to set up this difference. And so now what you're going to do is next you would evaluate all these values from the unit circle. So they don't say that. What they say is use an identity to simplify that right side. I wouldn't call that an identity. I would call it using the unit circle. And now how do we simplify these? This math is we would multiply each fraction set and then subtract the 2. So that would be this one. And then you should be able to go on to the next slide. Okay, so here I want you to actually do it on your own. So I would encourage you to pause the video and try the next 3 slides. Well, I will say do the next 2, cosine and sine, and then before you do the tangent one, watch what I have to say and then you can repause it. So for this slide, we're going to break up 285. What 2 angles on our unit circle? So it says use the sum identity instead of difference. Not that it should matter because you should get the same answer regardless, but so we'll say what 2 angles add to equal 285. So you look on your unit circle, guess and check. There's more than one answer, so if you pick a different one than me, that's fine. We should get the same answer in the end. But let's see what I picked. I picked 135 plus 150. So because it's addition, I'm going to set up my cosine sum formula using those angles. And then I'm going to evaluate those from the unit circle. So cosine of 135 is in the second quadrant. Cosine's negative square root of 2 over 2. Sine is positive square root of 2 over 2. And then 150 was also in the second quadrant, and cosine's negative square root of 3 over 2, and sine is 1/2. So I plugged in all those values. And now when I multiply the first 2 fractions, I know a negative times a negative becomes positive, and then I just multiplied the square root numbers, square root of 6 over 4. This is going to stay minus because this is positive, square root of 2 over 4. And then you just write that as one fraction because you can't actually subtract the numerator. So if you type that answer in, square root of 6 minus square root of 2 over 4 should give it to you. So what I would do is use this fraction button, then use the square root button, put 6, get out of the square root, put minus square root of 2 over 4. So then you can try sine. So if you haven't yet, pause the video and try this on your own. You can use those same 2 angles, just use the sine formula. So it's a little switched around. So now that you've tried it on your own, we can check it. So I use the same 2 formulas, but the same 2 angles, but it's a new formula. And so all these are switched around and it ends up being negative. So these first 2, because it's a positive times a negative, you keep that negative in front of the square root. And then this is also a negative, so that becomes minus. So negative square root of 6 minus square root of 2 over 4. If you type that answer in, it should give it to you. Let me just double check before we move on. So negative square root of 6 minus square root of 2 over 4. Okay, so for tangent, if you keep, I think I explained this, if you use those same two angles, let's see. And if we keep 135 and 150, you're going to have a fraction within a fraction, right? So because if you think about it, let me show you why. This isn't necessarily wrong, but it's not going to take your answer. So if you use 150, if we get tangent there, the denominator 2's will cancel, but you'll have 1 over negative square root of 3. And then you have to rationalize, but that's still going to be a fraction. And then you have a fraction within a fraction, which is kind of messy. So let's see if we could get around that by picking another set of angles. So what they did and what they want you to do to get the same answer they got is pick 225 plus 60. So you can pause the video and try that on your own with 225 and 60. So if you do that and you break it up, and we're going to use the tangent formula for addition, we have tangent of 225 and tangent of 60 we need to find. So if you go to 225, that's in the third quadrant, the tangent value there. Well, we know it's negative over a negative is going to end up being a positive, and they're the exact same number. So anything over itself is 1. So tangent of 225 is 1. And then what was it? 60, I believe. Yes. So now we need tangent of 60. So we go to 60 degrees in the first quadrant. Y over x, which the over 2's would simplify out. So it's square root of 3 over 1, which is just square root of 3, which is kind of nicer than having that fraction from the other one. So on the top, you end up with just 1 plus square root of 3. On the bottom, you have 1 minus 1 times square root of 3, which is just 1 minus square root of 3. And that's how they leave their answer. So if you type this in, get your fraction. 1, wasn't it plus on top? No, I already forgot. Yes. 1 plus square root of 3. And on the bottom, 1 minus square root of 3. Okay, if you do the other way, it's going to say it's incorrect if you use the other two angles because it's not going to match the format, which I don't think you have any issues with that on your test, though. Okay, so I'm going to have you try this one. And now it says obviously you should have to use a difference identity because 15 is smaller than the angles on the unit circle. So you're going to pick two angles on your unit circle that subtract to be 15. And then you're going to use your difference formula for each trig function. And so I will say on this one, if you pick the two angles from the first quadrant, so pause the video right now, come up with your two angles that subtract to equal 15 because I'm about to say it. Okay, so see if we pick the same ones. I think the easiest ones to pick would be 45 minus 30. If you pick 45 minus 30 and you use the difference formula, you can use the same 45 minus 30 for cosine. The next slide is sine. And the next slide is tangent. Okay, and you won't have any issues. You shouldn't, at least. So I'm going to have you try those 3 slides on your own. If you have any problems or it's not taking your answer, just send me a picture and let me know. But go ahead and pause the video and try those 3 slides to 22, and then we can pick up from there. Okay, so that's sum and difference. Now let's talk about cofunction identities. I don't think this one will take quite as long, but this would be a good spot to take a break if you need a break. So it says, you might have noticed that sometimes the cosine of one angle is the same as the sine of another. Can you think of an angle for which this is true? So if you think about it, we know that these ordered pairs for 60 degrees and 30 degrees are flip-flopped, right? The y value for 60 is the same as the x value for 30, and then vice versa. So what does that mean? The sine value for 60 is the cosine value for 30. That's all that this is saying. So then, is that a pattern on the unit circle that could create some identity? Probably, right? So on here, I'm going to show you what it wants, but then you're going to have to pause the video and finish this. because it's a little tedious, but it is good to see the pattern. So what it wants you to do is fill out this table. Theta is your angle. So you go to 0 on the unit circle, and you're going to type in the sine value, which ideally you would have your unit circle memorized, at least for those quadrant values. But in case you don't, here's 0 on the unit circle. The sine value would be the y value, which is also 0. So you type that in. Now, the next box, they want you to do 90 minus theta. Theta is this angle. Well, 90 minus 0 is still 90. So now you want to do cosine of whatever angle you put right here. So cosine of 90. So if we go to 90 degrees, the cosine value is the x value, which is 0. Okay, then you're going to go to 30 degrees. And now we want sine of theta, sine of 30. So 30 degrees, the y value is 1/2. So you're going to put 1/2. Now you're going to do 90 minus theta, 90 minus 30, which is 60. And then you're going to do cosine of 60. Well, if you go to 60 degrees and get the cosine value, that is 1/2. So maybe you notice the pattern, and that can help you fill this in, but go ahead and pause the video, and you're going to fill in this table, and you're going to fill in this table. It's very similar, it's just opposite. Cosine goes here, and then sine of this, whatever angle you get here, goes on the last box. And make sure you submit those, and then you can just give yourself some self-evaluation. So once you've completed that, you'll go on to the next slide. And it officially gives you your cofunction identity. So basically what you just discovered is cosine of 90 minus theta will just equal sine of theta. And then opposite, sine of 90 minus theta equals cosine theta. And then also tangent, which you didn't do this one, but it's giving it to you. I think it comes up with it here. The bottom is how they derived it. But tangent 90 minus theta equals cotangent theta. And then they come up with the last three, which are just the opposites and the reciprocals. Cotangent 90 minus theta equals tangent, and then cosecant 90 minus theta would equal secant theta, and vice versa, secant 90 minus theta equals cosecant theta. So those are all your cofunction identities that you have here, right? Because A, theta, X, that part doesn't matter. So how do they use those? Let me see what this says. I already forgot. Oh, okay, so this is explaining it. So it says the cofunction identities are useful for finding the measures of angles. For example, if you're given this formula, this equation, cosine 90 minus x equals square root of 3 over 2, and then they want x, which x is an angle because it's inside cosine, it's inside trig, to be between 0 and 90. That just means 0 and 90 is the first quadrant. They want your answer to be in the first quadrant. You could use a cofunction identity. So because we know cosine 90 minus x equals sine x, that's what our cofunction identity states, we can replace this whole left side, cosine 90 minus x, with just sine x. And so now we can say, okay, where, because they told us the first quadrant, so where in the first quadrant is the sine value square root of 3 over 2? So where in the first quadrant is the y value square root of 3 over 2? Well, at 60 degrees. So that would be your answer for x. And then they just give you another example here. It says, what if you have cotangent? Well, hold on. The cofunction identities can also help you evaluate an expression such as cotangent 60. You could rewrite 60 as 90 minus 30, right? And then we know that 90 minus cotangent 90 minus 30, 30 is in place of x, or a if you're using your formula chart. So then that would be just the same as tangent 30, which then tangent 30 from the unit circle, you would have to rationalize it, but it would end up being square root of 3 over 3. So let's do some actual problems and see if that helps. So if you want to try this one on your own, go ahead and pause it. But we can do this together. I think I did it on a PowerPoint slide. So what are we going to do first is anytime you see this 90 minus x, you're going to try to use a cofunction identity. So what is cotangent 90 minus x the same as? So I'm going to look for that on my formula chart. Cotangent 90 minus a equals tangent a. So I can replace that with tangent a. So I replaced that with tangent x equals square root of 3. So I'm going to ask myself, where on my unit circle does tangent have a value of square root of 3, which I could also think about that as square root of 3 over 1. This is why I think it helps if you go through and write those simplified tangent and cotangent values on your unit circles. You don't have to think about this every time, but we can. So I would start in the first quadrant. How am I going to get square root of 3 over 1? Well, I'm going to do y over x. So I want square root of 3 to be on the top for my y value. So that would be this fraction over 1/2, because those 2's will cancel. And you'll have square root of 3 over 1, which is square root of 3. So it's 60 degrees. Is there anywhere else on the unit circle where tangent is positive square root of 3? Tangent is also going to be positive in the third quadrant, because y over x, negative over a negative, ends up being positive. So you could also take 240 degrees if you do y over x. That would also be positive square root of 3 once you simplify it. So technically your answer could either be 60 degrees or 240 degrees. But if you look, it's multiple choice. They just want 60 degrees. So hopefully that makes sense. If not, let me know. So here they're just rewriting. You're not actually solving like we did in the last problem. So think about this. Is this the same as the cofunction identities we have on our formula chart? What's different? Well, this pi over 2, is that the same thing? Well, if you look on your unit circle, we know 90 degrees is the same thing as pi over 2 radians. So you could technically rewrite all these cofunction identities with pi over 2 instead of 90 degrees. So that's the same thing. Anytime you see that, just know it's still a cofunction identity. So think about this as 90 degrees minus x. What is that equivalent to? Well, sine of 90 degrees minus x is this one, and that equals cosine x, or a, but because they use x, we're going to use x. So you're going to put cosine x. And then you should be able to move on. So you can try this one. Just make sure you match the letter. Whatever letter they put here, you need to use. So whether it's an A, an X, a Y, a theta. So cosecant pi over 2 minus theta. Well, I'm going to look for that on my chart. Cosecant, I know pi over 2 is just 90. So cosecant 90 minus theta, or A, is equivalent to secant. So I'm going to type secant of theta. So if you're not understanding where I'm getting this answer from the formula chart, you need to make sure you reach out to me and let me know. Okay, so this one, try this on your own. You got to do some simplifying in here and then just rewrite using a cofunction identity like we have before. So pause the video because I'm about to show the answer, but I want you to try it on your own. So the first thing you would have to do is distribute and clean up that inside. So if I distribute this minus sign, it becomes 120 minus 30 minus A. And then 120 minus 30 I know is 90. So it becomes cosine 90 minus A, which if you look for that on your formula chart, cosine 90 minus A is at the top, and that equals sine of A. So that's the way to rewrite that problem. So always make sure you keep the variable the same. Well, it's going to do that thing where it does with y'all, where it doesn't load. If you ever have that issue, you just got to be patient and probably log. If you get this, log out, give it some time, and then relog in and try again. Fortunately for me, I can keep going, but I know y'all can't. So, okay, so summary. Going back to that original problem, if you remember, is we were talking about how do we know the height of this big triangle. So we know now that what we could do is if we add these two angles together, that would be 75. And so because we're adding two angles together to equal that original angle, we can use a sum formula for tangent. And so if we do that, tangent of 45 is 1, tangent of 30 is, if you go to your unit circle, 30 degrees is right here. If I do y over x, that's going to be, maybe I should type this out. Well, I don't know. That's going to take too much time. You can simplify this on your own, but you're going to have 1/2 over square root of 3 over 2. So those over 2's would cancel. So you're left with 1 over square root of 3. And then if you rationalize that, you would get square root of 3 over 3. So that is where they got that answer. And then they just left it like this. And so that what they also said is we also know tangent 75 separately, not using what you just did, is going to be equivalent to whatever opposite over adjacent is, using SOHCAHTOA. So if you're using this big triangle, because we're using the 75-degree angle, the opposite leg would be this long side, which would be the h plus 5. And the adjacent side would be this bottom leg, which is 5. So that's what they did here. So now you have these two facts, that tangent of 75 equals this using opposite over adjacent, and tangent 75 equals this using your sum formula. So because they're both equal to tangent 75, then they have to both equal each other, right? They both equal the same thing, so you set them equal to each other. And then they just did some algebra, so they first multiplied by the 5 to move it over. So when you multiply by the 5, it goes to the numerator, and they distributed it. And then they subtracted the 5 to get h alone. So they know what h is now, this top part of this side. So if you want to know the whole height of the tower, it's this h value that we just got plus the 5 at the bottom, and you get this, which you could type that in the calculator and get 18.66. So if you have any questions on that, let me know. There isn't a question, I don't think, on y'all's test where you have to do something like that. Okay, so here's just a summary of all the identities. You have all these. They use U and V instead of A and B, and they use theta here instead of A, but these are the same ones that you have on your formula identity chart. And then that's just a summary that you can watch, and then congratulations, that's the tutorial. Now, before I let y'all go, I want to give you some examples that will help you with your test. Now, the way they do the test is there's 10 questions, and then they randomly select 5 to give you for your test. So I'm about to give you, I went through them, and most of them, if the tutorial made sense, you should be able to do those questions. But there's a couple that seemed a little far-fetched that didn't exactly line up with an example. So I'm going to go through and do those. I made examples that are very similar. There's one that's the same because there's no way that I could come up with an example that would help. So you might not get these questions though. So you might not need these, but you might need all of them. So make sure you watch these and you're ready for when you go do your test. So the first example I wanted to give you was a question where they give you sine of x and they give you cosine y. And then they also tell you if angle x is in the first quadrant and angle y is in the third quadrant, what's cosine of x plus y? So we know we're going to be using our sum identity to find cosine of x plus y. So if you skip down here, I set up my sum identity for cosine. Hopefully we're all good there by now. Just go back, instead of a and b, it's just x and y. So if you think about this, I already know sine x and I know cosine y, but I need to know also cosine x and sine y to be able to fill in all that information. So I'm going to go back, and this is the first step I put on here, determine the other sine and cosine value for each angle. So for angle x, they gave me my sine x, and they also gave you that it's in quadrant 1. So think about it. If you go look at quadrant 1 and look where the sine value is square root of 3 over 2, and what would also be the cosine value there. So we're going to go to our unit circle, quadrant 1, and look, okay, sine value square root of 3 over 2 would be right here at 60 degrees. Now what's the cosine value there? 1/2. So cosine of x is 1/2. Notice you don't actually need the angle. We don't need x. We need cosine x, which would be 1/2. So now I know cosine x is 1/2. Now we're going to do something similar for angle y. We know cosine y is negative 1/2, and it's in quadrant 3. So now let's find what sine y would be. So you're going to go to your unit circle in quadrant 3, should be down here, and look for a cosine value of -1/2, which cosines the x value, which would be right here at 240 degrees. But again, we don't need the 240, we need the sine value there, which would be -√3/2. So sine of y is -√3/2. So now you have all your components, you just plug it into the formula. So we set up our sum formula, and now we know cosine x was +1/2 times cosine y was -1/2, and then it's minus sine of x is √3/2 times sine of y is -√3/2. So when I multiply these, the first two, 1/2 times -1/2 is -1/4. And then here, √3/2 times -√3/2 would be a negative. So then you have minus a negative, which I changed to a positive, so it's plus. And then you multiply the square root. So √3 times √3 is square root of 9 over 2 times 2 is 4. So then we're going to add the numerators, right? So normally we just keep it like that, but in this case, we know the square root of 9 is 3. So I could write that as -1 plus 3 on the top, which is then equivalent to 2. So we have 2 over 4, which is 1/2. So if you have any questions on that example before you take your test, let me know. Okay, this next example is like the crazy one where it's like, how would you even know to do this unless you were given an example? So in this problem, they start with sine of x plus y over sine of x minus y, and they ask you to simplify it. So we know you could probably figure out on your own to use sum and difference formula on the top and bottom. So we did the formula for x plus y on top and x minus y on bottom. So the only thing that's different is it's plus on top, minus on bottom. So then this is the part that's kind of weird, but anytime you have a fraction, as long as you do multiply the top and bottom by the same thing, it's valid, right? You kept it equivalent. So to simplify this, we're going to multiply the top and bottom both by 1 over cosine x cosine y. So if I do that to the top and bottom, I'm going to have to distribute it to every single term. So if I multiply every term by 1 over cosine x cosine y, you're basically going to be dividing by cosine x cosine y. So every single term is now being divided by cosine x cosine y. And then you can start to see what simplifies out. So the first fraction, the cosine y's would cross off. Plus the second fraction, the cosine x's would cross off. And then on the bottom, the first fraction, cosine y's would cross off, minus the second fraction on the bottom, cosine x's would cross off. So you're left with this next level. And now we can use, quotient, quotient identity would let us simplify all these fractions because sine over cosine is tangent. Just make sure you keep the letter the same, right? Sine x over cosine x is tangent x, plus sine y over cosine y is tangent y. And then similarly on the bottom, it becomes tangent x minus tangent y. And that is how they want the answer. Hopefully that helps you if you end up with that question on your test. Okay, one more is I just wanted to show you one where it was rationalized. We already talked about this, but just in case it didn't click. So let's say they started with tangent of 90 minus x equals square root of 3 over 3. Well, we could use a cofunction identity to replace tangent 90 minus x with cotangent x. So then you're asking yourself, okay, where on the unit circle does cotangent x equal square root of 3 over 3? And the hint is that it's rationalized. So you could go to your first quadrant and go find the cotangent values. So if I do cotangent is x over y. So if I start at 60 degrees and I do x over y, that would be 1 over square root of 3, right? Because the over 2's would simplify out. And then you'd rationalize that, and you would get square root of 3 over 3 when you rationalize. So I think, hold on, wrong slide. So that's what I showed you here. If you take 60 degrees, you have this order pair. And then if you do cotangent x over y, because they're both over 2, the denominator is 2 for both of them, it simplifies, and you'll have just 1 over square root of 3. Then you rationalize by multiplying the top and bottom both by square root of 3, and you end up with square root of 3 over 3, which is what we were looking for. So x would be 60. Now I made a note that it could also be 240, right? Because at 240, the order pair is negative, negative. So when you put it over each other, it also becomes positive square root of 3 over 3. But I think that's a multiple choice question where so it'll only have one of those options. Or it'll tell you it wants it in the first quadrant or something like that. Okay, I think that is everything. So if you have any questions, please let me know. But make sure you have these formulas in front of you, a unit circle in front of you, and good luck. I am available for questions. I'll be available also Wednesday at 1 p.m. for a Google Meet for any questions you would like to ask in person. But if you're having any technology issues, let me know and I will try to help to the best of my ability. Y'all have a great rest of your day. Let me see.